Alright guys, welcome to lesson 6. We're going to do integration, but today we're doing it with trig functions, and most of it will actually involve u substitution. So let's go ahead and jump in here. So it's a little fuzzy here, it doesn't look great. But remember our derivatives. Okay, so the derivative of sine was cosine. The derivative of cosine was negative sine. The derivative of tangent was secant squared. Derivative of cotangent was negative cosecant squared. The derivative of secant was secant tangent, and the derivative of cosecant was negative cosecant cotangent, right? So now we're going to be working backwards today. So in other words, people always mix up the sine and cosine one. So we've gotten so used to saying sine gives cosine and cosine gives negative sine, but now we're going to work backwards. So we're going to start here. And the integral of that is going to take us back to sine. It's not going to be negative. But when we integrate sine, pretend that negative is not there. When we go back to cosine, that will make a negative because it's the opposite sign, right? So things to think about there. So here's our integrals. So the integral of cosine is sine. The integral of sine is negative cosine. And the integral of secant squared is tangent. And then so on and so forth. These ones are kind of weird. The integral of secant tangent is secant, and the integral of cosecant cotangent is negative cosecant. If it doesn't fit one of these 6 patterns, then for the time being, we can say that it's not really relevant. There's, you could have other trig things that you're trying to integrate. Sometimes you just can't integrate them, but for now, these are the 6 we're going to stick to. Now, when we're doing these, we're going to do u substitution, because if I didn't have u substitution, then it'd be kind of pointless. It'd basically just be you copying the sheet that we just had. So, all these problems are going to be u sub problems. So, let's begin here. So, the first thing we want to do is we want to find our inside function. So, there it is. And we want to set that equal to u. Next, we want to find the derivative of u with respect to x. It's been a little while since we've found a derivative of an exponential function, so let's review how to do that. So when you find the derivative of an exponential function with the base of e like that, the derivative is just the same thing all over again, but you have to multiply it by the derivative of its power as well. So the derivative of 4x is 4. So that would be the derivative of u with respect to x. This 4 just goes away whenever you take the derivative of that, right? Next, we want to get the dx by itself. So now we're ready to do our u substitution. So we're going to come back over here, and we're just going to be replacing everything in there with u's where we can. So for now, the negative 8e to the 4x is just going to stay there, but it's going to go away in a minute. But the secant squared, the parenthesis part, we can replace this whole thing here with a u, because that's what we said u equals, and we can replace the dx with a du over 4e to the 4x. Now, the e to the 4x's cancel out completely, so now our x's are gone, but the 4 also goes right into that 8 there twice. So here's what I have now. I've got negative 2 secant squared u to u. If you want, you can go this extra step. If you ever have a constant in the front, you could just take that out of the integral, because integrals don't affect constants. They just sit there, just like with derivatives. It's called the constant multiple rule. So now, let's look back at our chart. What is the integral of secant squared u? Go ahead and go back to that last page real quick. The integral of secant squared x is tangent x, right? But instead of x, we're doing u. So the integral of secant squared u is going to be tangent u. So after you integrate, the integral symbol goes away. Don't forget your plus c. And then, of course, the last step is to replace the u with what u was originally, which was e 4x plus 4. And I had a little smudge there that shouldn't be there, so I'll erase that. But anyway, there's your final answer. Like that. So basically, same thing, you know. Set u equal to the inside, find the derivative. I made the derivative a little bit harder this time for that. Get the dx by itself, do your u substitution. Everything should cancel out like usual. A little difference that might be helpful with these trig subs is to take the constant and just bring it outside of the integral. From there, you should be able just to find the correct integration process using the chart that I gave you for the integrals at the beginning of class. All right, let's go ahead and move on to number 2 here. So I'll teach with questioning here. So my question to you is, what is the u of this problem? Hopefully you guys were thinking in your mind, well, Mr. Bailey, the u would be this thing. Now, I don't like the way this looks. You know what this looks like to me? It looks like it says -1 plus ln minus 3x. Well, you can't subtract something from ln, so this is not ln minus 3x. What this is this is ln of 3x. So you might want to throw some parentheses on there. Okay, so let's go ahead and find du dx. So I would encourage you guys to go ahead and try to find the derivative of this on your own. Go ahead and try it. What would you get? If you need to pause the video, go ahead. But if you were to take the derivative, the -1 goes away because it's a constant. When you take the derivative of an ln, it's 1 over whatever's on the inside times the derivative of the inside. So the -3's cancel, and what I'm left with is 1 over x. Now here's another interesting thing, a little bit different than usual. We need to get the dx by itself. Now this is different. We haven't seen one like this before, but just remember your algebra. Try to get dx by itself. Give it a shot. Pause the video here and give it a try. So what you should have done was you should have multiplied both sides by a dx first. Okay? So this and this cancel, and I'm left with du is equal to 1 over, you could say dx over x if you want. Dx like top times top, bottom times bottom. So dx over x. The next thing you want to do is you're going to multiply both sides by x. Okay? So now I have x du is equal to dx. Now, I don't know if anybody was wondering this, but I'll address it. Some of you guys might think, well, wait a minute, but can't we cross these x's off? And the answer is no. And the reason why is because this is not d times x on the top. Okay, that's not what that means. This is actually one whole thing by itself. They're not separable. You can't take them apart. They go together. So that's not like a d being multiplied by an x. That's a dx. That's a thing all by itself. So no, it cannot be reduced with the x, just so you know. But anyway, there it is. So this one was a little bit different. And isn't that interesting too? Like usually we have du over something, but in this case it's du times something. So this one was a little bit weird because of the way that it's the fact that we have an ln. So ln's will do that to you. Okay, so let's continue. So now I know what dx equals, and I also know what u equals. So I'm going to go ahead and do my u substitution. I'm going to replace this whole thing here with a u, and I'm going to replace this thing here with x du. And we had this extra x on the bottom there, but guess what? That's not a problem. It's about ready to go away. So the x on the bottom is going to cancel out with this x on the top that's with the du. those ones do cancel out because that is x times du. So those ones will cancel out. So now what I'm left with is this. And that almost fits one of our little rules on the other page there. Let's go ahead and take a look at the other page. Let me back up a little bit. Oh, actually it does fit one exactly. There it is. So the integral of cosecant squared x is negative cotangent x. So there it is. So we have our answer. Well, not the final answer, but we have the right integral. So the integral of cosecant squared is going to be cotangent plus c. And now we're going to replace the u with what it was originally. And the u was originally -1 plus ln of -3. And I like the parentheses around the 3x, but they probably wouldn't have it in the final answer on my multiple choice part. So this one was kind of weird. It was hard in a few ways. What made this one hard was mainly all this stuff over here. Okay, since we had an ln, the derivative came out funny. And since the derivative came out funny, the way you get dx by itself was a little bit funny. But after that, it was all pretty much old news, stuff we've done before. All right, let's take a look at the last one here. This one also has an interesting little twist to it. Let's see. Now, I really don't like the way that this one is written at all. It's really hard to see what we're even looking at, honestly. Man. And now, so here's your calculus teacher who's been teaching this class for years, and then I still look at number 3, and it still makes my brain spin. I have no idea what I'm looking at. But that's the beauty of u substitution. Let's just trust it. So long as you know how to do u substitution, it's going to help you on this problem, okay? So let's follow through with the steps. What is the u? The u is the one in the parentheses. It's tangent of -x. Now remember, that's not tangent minus x. You can't subtract a number from tangent. Tangent's not a number, okay? It's tangent of x, -x. So now we're going to take the derivative. So this derivative might be a little tricky for you also. So let's see how you do with it. Pause the video and see if you can find the derivative. It is a chain rule because we have an inside function, which is -1x, and an outside. So see if you can find the derivative of tangent of -x. Okay, so the derivative of the outside is secant squared. The derivative of the inside is -1. And I'm just going to put that in the front there as a negative. All right, now we want to get dx by itself. Now that one's not too weird. I mean, honestly, it's pretty much what we've been doing from all the other problems. Just put it on the bottom of the du there. And dx over here. Pretty straightforward. All right, so now this ugly, nasty mess here is about ready to look a lot prettier. Okay, so here we go. But you got to know where to put things in order to make it look prettier. So remember, we're going to replace tangent of -x with u. So I'm going to put a u here and here. There's 2 places I'm going to put a u because there's 2 of those in there. There's 2 tangents of -x's. Okay. This thing I can't do anything with this yet, but here we go. So let's write all that. So a negative secant squared, and then they have a minus x, but it's not a minus x. Really, it's an of x, just so you know. It looks like a minus x. And then we have secant, and there's my u. So I'm going to replace that with u, and then tangent, and then another u, and then we have du over secant negative. I ran out of space. I need to make a little more space for myself. Just a second. I guess I'll just have to rewrite it. Sorry guys, just a second. Alright, so we had integral no. There it is. Okay, now there's one more x left there, right? But they cancel. Negative secant squared of negative x, negative secant squared of negative x. Those two things completely disappear, and here's what I'm left with. Once you get there, you should be able to go back to the last slide to find out which integral it is. If you look at your slide, you'll see that the integral of secant tangent is secant. And then if we just replace the u with what u was tangent of negative x. Okay? So that was a really nasty problem. It looked ugly, but so what made it hard was just how there's just so much crud there. But the good news is that just go with it. Find the inside function, make that your u, do the derivative. The derivative is a little tricky on this one, and then do your u substitution. After you do your u substitution, it should look nice and easy. It should be a little bit more straightforward and to the point. Alright, so we're going to let you guys try a couple of these. So go ahead and try these things, do as much of them as you can, and then I will put up the answers shortly after. So here's the answer, number 1. If you need to study that, pause the video and look at it, but that's what you should have gotten for number 1. Let's go ahead and take a look at number 2. And what's boxed down there is the answer to number 2. Something I want to draw you guys' attention to, though, is that when you do your u substitution, the e to the 3x's and the 3's cancel out, but that negative doesn't cancel out. That negative is still there. And so I have it right here on this problem, and then I took it out to the front because it's like a -1, so it's like a constant. You can take it out if you want to. You don't have to, but you can. Okay, now the integral of sine is negative cosine, but there's a negative in the front, so you have these double negatives which cancel each other out, and so you're ultimately left with a positive one, and then you just replace the u back in. So that little negative gave us a run for our money there, so pay attention to that. Alright, let's go ahead and take a look at the last one there. Alright, and here is our last one here. The u in this case would be the cosine of 3x. Taking the derivative of that, you would have to do a chain rule. The derivative of cosine is negative sine, and the derivative of 3x is 3. So if you multiply 3 times negative sine, you get negative 3 sine 3x. And then getting the dx by itself, you get what we have here. And then doing our u substitution, we're going to replace this whole thing with u, and we're going to replace the dx with du over negative 3 sine x. And then this piece in the front is just going to stay there, but the good news is it cancels out. The sine 3x cancels with the sine 3x. The negative 3 goes into the 15 negative 5 times. So that's what we're left with, and we like to put those constants out in the front of the integral. And then if you take the integral of sine, you get negative cosine. So you have a negative 5 being multiplied with a negative cosine, which makes a positive 5 cosine. And then putting the u back in, you get 5 cosine of 3x. Now, just so you guys know, this is not cosine times cosine. Okay, this is cosine of cosine, which means you're plugging a cosine into a cosine. It's not the same thing as multiplying two cosines. So you can't write this as cosine squared, just so you know. That would be like you're multiplying them, but we're not. We're actually plugging one into another. So there's that one. All right. So that's one thing. Let's go ahead and take a look at doing some definite integrals with trig functions now. We'll start easy and then we'll do a slightly more challenging one. Okay, so this is where you want to know your unit circle. Okay. All right. So first thing that we're going to do, we want to integrate is or do a definite integrals. Nothing new here. It's just that what's new is that we're doing trig with it. So we want to do the fundamental theorem of calculus on this. We don't need to do any kind of u substitution or anything. This thing's ready to be integrated. We already know what the integral of cosine is. The integral of cosine, according to all of our notes from earlier today, is positive sine. Okay, so that's our integral. So we already know what the integral of cosine is. So step one is to integrate cosine, which gives me sine. And when you do definite integrals, you don't need a c, right? Now that I've integrated, we don't need the integral symbol anymore. We just put brackets and we move the upper and lower limits of integration to the right. Now we do the fundamental theorem of calculus where we do bracket minus bracket with parentheses, and we plug in the top one first, bottom one next. Now if this was a free response question, you guys, I would stop right here, because at that point your calculus is over. From here on out it's just basic math. But if it's a multiple choice, you need to know how to get your answer. All right? Now, how are you guys going to do this without looking at your chart? Now, I know you guys can look at your chart, but I'm going to show you the thought process that goes through Mr. Bailey's head. Mr. Bailey sees in his head a circle. And the first thing he does is he wonders, where is pi located? Pi is right here. That's pi radians. And then pi over 3 is up here. That's pi over 3 radians. And I know that sine is the y value. So now I'm wondering, what is the y value for these points? And once again, I've memorized those as well. The y value here is easy. It's just 0. The y value up here is a little nastier. It's radical 3 over 2. And so 0 take away radical 3 over 2 is negative radical 3 over 2. And there's my final answer. So this would be a good multiple choice answer, but if you're doing an FRQ, stop there so you don't get the wrong answer. But if you're doing multiple choice, take it home. Okay? Now in your homework, it's not an FRQ or a multiple choice, but I would say practice taking it all the way, mine as well, just so that you can be sure you got the right answer. All right. Now let's take a look at the next one here. So same thing, we're going to start by integrating, and once again, that's ready to be integrated. We already have a rule for that. What's the integral of secant tangent? Hopefully you know it is secant. Upper limit here, lower limit here. Okay, now unfortunately these ones are negatives, but we'll get to that in a minute. Alright, so let's plug these in really quick. So these are negative angles. So once again, if this was an FRQ, stop right there. But, and when I say FRQ, you guys, I mean like on a test. I mean, if it's not a test, practice. Go as far as you can. But on a test, stop there. Don't go any further. Okay, because anything beyond this is not calculus, it's trig. But we're going to go further because I want you guys to see how to do this. So first of all, here's one thing you guys need to know. What is a negative radian? Well, here's my unit circle. I know where positive pi over 6 is. Positive pi over 6 is right here. But this is negative pi over 6. Negative angles, instead of going counterclockwise, go clockwise. So it's mirrored down here. So this is actually negative pi over 6 right here. Now, if you're actually looking at the unit circle, negative pi over 6 is in the same exact spot that 11 pi over 6 is in. So really what we're looking at here is 11 pi over 6. Okay, so secant of negative pi over 6 is the same thing as secant of 11 pi over 6. These are called coterminal angles. They're at the same spot on the unit circle, so they're going to give you the same answers. So the only difference for negative angles is that you go downwards instead of upwards whenever you're moving along the circle. Anyway, so now we need to do secant of 11 pi over 6. So Mr. Bailey now remembers that secant is the reciprocal of the cosine value. So the cosine value is the x value. So secant is going to be the reciprocal of the x value. What's the x value of this point? Well, I've taken the time to memorize it, and I know that it's radical 3 over 2. We don't care about the y right now, but I do know that the x value there is radical 3 over 2. So secant of 11 pi over 6, the reciprocal of that would be 2 over radical 3. Okay? Now, we don't usually leave our answer with radicals on the bottom, so we would have to rationalize that. And what we would end up with is this. So here's your final answer. So that one's pretty complicated. First of all, you have to know that a negative angle means you go downwards, and you have to know what angle on the unit circle that's going to land on usually. Then you have to know that secant is the reciprocal of the x value, and then you have to know to rationalize it. So there's a lot going on there. So this one is 2 radical 3 over 3. I would encourage you guys to try to do this one. Now I know you guys can look at your chart to get the answer right away. I also know that you can even look at your unit circle, but if you've some of you guys have taken on that challenge of doing the unit circle, so you should know, you should be able to do that in your head. It will take you longer than me, probably, unless you're just really awesome. But either way, you should be practicing the art of doing that in your head. Now, for those of you guys who haven't taken the time to memorize your unit circle, what I would do is I would say pull out your unit circle and work off of the unit circle to get the answer. But don't go to that chart. That chart's a nice way to check your answer to make sure you're right, but I wouldn't use that chart because you're not memorizing the chart. Instead, use the unit circle that I gave you a while back. So go ahead and try that. Pause the video here and see what you get, and then I'll walk you through what the answer is when you unpause it. All right, here we go. So I asked you guys to work on secant of negative pi over 4. Well, first of all, I know where a positive pi over 4 is. That's this one up here. But a negative pi over 4 would be the one dead smack in the middle of the bottom quadrant right here. So secant of negative pi over 4 is in the same exact spot as what we have on our unit circle, known as 7 pi over 4. And now secant, as I said before, it's the reciprocal of the x value. Now the x value at that point is radical 2 over 2. We don't care about the y value right now. So the reciprocal of that is going to be 2 over radical 2, and therefore we need to rationalize it. And what you would get is 2 radical 2 over 2. The 2's cancel, and the final answer is radical 2. Now, I could say we can just stop there, but hey, I'm going to torture you a little bit. We can actually put those together into a single number now. So here we go. Let's do that. So I have 2 radical 3 over 3 minus radical 2. Well, how do we put these together? Well, we need a common denominator. So what I would do is I would multiply the top and the bottom here by 3. And what that's going to give me is the following. Now, since these have different square roots, it's impossible for me to combine these together. But what I can do is I can put them together in one single numerator over a common denominator. So that would be the most simplified answer. And at this point, you guys are thinking, why did I sign up for calculus? Well, believe it or not, you're not frustrated with the calculus, you guys. We were done with the calculus by the time we got right here. What you're wondering is, dang it, why did I have to not know my pre-calculus? That's what you really should be saying. All right, anyway, so that is definite integrals with trig functions. So here's a couple for you guys. Go ahead and pause the video, see if you guys can get the actual answers for these. And you can also check your answer with a calculator. The only issue is that most calculators will give your answers to you in the form of decimals. And while we're on that topic, you guys, just so you know that when you're using a graphing calculator, your calculator needs to be set to radians and not degrees. If your calculator is ever set to degrees, you're going to get all the wrong answers and you'll fail your test. So never use degrees in this class. We always do radians. Same thing on the AP test. Anyway, I digress. Your calculator, if it's a TI-84 or 83, if you just push second plus 712 and clear your calculator, it automatically resets it back to radians. But you can also do it through the mode button. But I've said too much. I'll be quiet. I'm going to let you guys go ahead and pause the video here and work on these problems. When you unpause it, you'll see the solutions. All right. So these are the answers. Now, question, where should I stop in order to, if it was an FRQ test, where would I have stopped so I don't have to go any further? Hopefully you guys know you would stop here. And hopefully everybody got to that point and you were perfectly right. If you didn't even get there, then you need to come see me during office hours and get some help, because that's just the basic calculus stuff there. Now the rest of that's the trig stuff. Cosine of pi is -1. Cosine of pi over 6 is radical 3 over 2. You got some double negatives you got to work with, and then a common denominator to work with down here. And there's your final answer for a multiple choice test, would be this one. Let's take a look at number 2. Now on number 2, you'll notice I started by putting that -2 outside the brackets there. I didn't like it on the inside. The integral of cosecant squared is negative cotangent x. And then we did the fundamental theorem of calculus. Now notice here that -2 in front of the brackets, it needs to go in front of both pairs of brackets, just so you know. So we have -2 bracket minus -2 bracket. And then we plug in the pi over 3 and the pi over 4. Cotangent of pi over 3 is radical 3 over 3. Cotangent of pi over 4 is -1. Multiplication gives me this, and then finally common denominators give me that. But once again, you guys should have been able to get to here. If you didn't get to that FRQ answer there, then you need to work on it a little bit more. Okay. As for this part, I would say, keep at it. It's going to take some practice for you guys to get used to it. I'd be really, if you got these answers, that's awesome. You're doing really well. I would expect maybe 2 or 3 of you guys are there. Most of you guys are probably okay with getting here. Some of you guys are probably really struggling though with this bottom half, the trig stuff, and I understand that. If you guys are the people who have submitted the unit circle extra credit, I would expect that you are the people who got at least this far, if not that far. Okay. Anyway, that being said, I think we're done for the day with this lesson, so let me make sure of that. Oh, well, there's that unit circle. I didn't know I put that in there. That's helpful. You guys can use this, by the way. The black ones are the tangent values, and as you know, sine is the y value, cosine is the x, secant is the reciprocal of x, cosecant is the reciprocal of y, so you can use all those. Anyway, I think that does it. I think we're good for the day. We'll see you guys next time.